2150, object orientation. I hope you are all doing great today. I hope that you're all doing great today. If you didn't see this already, if you didn't see it already, the due date for the assignment is Friday. Yeah. That's me, begging for applause here. The due date is Friday. I understand there's also like a 2280 test or something, like today? It's, oh my God, okay. Wow, it's the middle of the term. I'm sorry. Yeah, so the due date is due on, the assignment is due on Wednesday. Or, oh my God, the assignment is due on Friday. The assignment is due on Friday. It's due yesterday. It's due on Friday. So there's a little bit of a break there, a little bit of a break. Today, what I want to do is finish up with the Orthodox Canonical Class Form. I want to stop trying to say this. I want to stop trying to say it because I keep saying it and it's really hard to say. What I want to do today is finish up with copy constructors. So the place where we left off last time was that we had just added a copy constructor for our Pokemon type. The end goal here was that we wanted the Pokemon to be able to have ownership taken by the trainer class. So we want, when a trainer has a Pokemon instance added to it, we want the responsibility of releasing that memory to be on the part of the Pokemon trainer itself, as opposed to whatever class owned it in the first place. So that's where we're going today with copy constructors. I want to do the assignment operator. And the assignment operator is, it's basically just like barfing symbols on the screen until something happens in the way that we want it to happen. I apologize for the syntax that C++ uses to do this, but I am not the person who created the C++ language, so take that for what it's worth. I think that the syntax for assignment operators and just operator overloading in general in C++ is terrible. But it is what it is. So we'll take a look at that. And then what I want to do is spend some time talking about substitution and the forms of inheritance. One of the things that we talked about quite a lot earlier in the term was this idea of solid design principles. So single responsibility, and then something else, and then L, and then something else, and then something else. Today, we're going to be talking about what L is. We're going to be talking about this idea of the principle of substitution. And then we're going to talk about the forms of inheritance. There's a bunch of different things that you can use inheritance to do to accomplish things in a design perspective. This is going to be a lot of like definitions of terms and the structure that inheritance is used in. And then we're going to be thinking about whether or not these different forms of inheritance are substitutable. So whether they satisfy this principle of substitution. So first things first, Orthodox Canonical Class Form. I'm not going to put the slide in anymore. I don't want to say this anymore. It's a mouthful. The thing that we're focusing on right now is copy constructor and an assignment operator. So copy constructor, just to really quickly remind you of this idea, we're taking a reference object. So remember, we've got this new kind of type that we have in C++ that's not really present in languages like C and Java. We actually have a type that is a reference object. And we're going to write a constructor that's going to take all of these properties that are within that instance and then duplicate them. So my goal here right now is to just finish up this example. I want our trainer class to be able to take ownership of an instance of Pokemon by making a copy of it, by using the copy constructor that we started last time. So let's take a look. The very first thing I want to do is address a question that was asked last time before we get into the copy constructor stuff. And the question was, how do we add a static class variable to a class in C++? The way that you do that is for a string specifically. So for things that are not primitive types. Primitive types, you don't have to do this, but for non-primitive types like strings, which are objects, you first declare them. And then after you declare it, you have to initialize it separately. So on line 6 here is where I'm initializing that constant string. So in the class definition itself, I have declared this as a static const. So static is once per class, once per file. Const, I'm not going to change it. It's a constant value. It's of type string, and it has this name. And then this is private right now, but you can make this a public variable by putting it in the public section. And then this, to initialize it down here in the actual implementation, you provide a value for it by saying const, so the type declaration, then the name using the prefix of the class itself, and then assigning a value to it. If you're using C++ 17, and I'm not sure if Clang++ uses 17 by default or 14 by default, so you'll have to try this on your own. You can do this all in one line using an extra keyword here inline, but you have to specify that you're using C++ 17 to get that. Good, good. Okay, so what we want to do is let's take a look at Pokemon here. This is where we started to create that, that copy constructor. And the way that we initially did that was that we added this new Pokemon const, Pokemon, and then ampersand. We're putting that ampersand in a strange place compared to where we were doing this with C before. And this is declaring this as a type of reference argument to this reference parameter to this method. We're adding the const here to basically say, we are not going to change this, and I want to be forbidden from changing it in my own code. I don't want to accidentally replace the contents of memory that are here. So by putting const there, it's saying you just can't do this. You're forbidden from doing it by the compiler. In Pokemon.cpp, I've added some comments here, and I put a couple of things in here. We're copying things from the other object that we are passed into the copy constructor. So we declare this similarly to what we were doing with other constructors. We have the same parameter type that we have declared in the header file. I'm using a mixture of initializer and like regular initialization syntax just to show that it's possible to use both, but we wouldn't normally mix them together. We would just pick one or the other. When we have these reference types, remember, we use the dot notation as opposed to the arrow notation. This is an actual thing. It's an address that we're passing around, so we can use the dot notation on this to get the values that we want from that. I'm going to leave this as a question for you, just as a kind of general design question, which is the original trainer type is a pointer to another trainer. It's a pointer to a trainer. And then thinking about what we're thinking about with ownership of values, does it actually make sense for this Pokemon to take ownership of this or not? Should it be deleted? It's a pointer type in this Pokemon class. And I'll leave this for you to think about. I'm going to move on to what I want to actually do. And what I want to actually do here is I want to go on and take a look at trainer itself. So one of the options that we have on trainer is that we are able to add a Pokemon to a trainer. Right now, when we are calling the destructor in trainer, so I'm going to go to the implementation here. I'm going to pop this over to the side just so we can see them both at the same time. In the destructor for trainer, what we have right now is that we are assuming that the trainer is taking ownership of these objects. So we're passing pointers to Pokemon, to the add Pokemon method. And we're making an assumption that the trainer type is taking ownership of those pointers. We're making that assumption, and then we're just calling delete on those pointers, on the pointers that we've been given to these Pokemon instances. The problem that we have with that is that when we are using this, so here's testtrainer.cpp. When we're using this, we can pass pointers to Pokemon, like on line 19 there, which have been declared as stack allocated objects. And we can't transfer ownership of stack allocated objects. A stack allocated object is always going to be owned by its enclosing scope, which in this case is the main function. So we're not allowed to transfer ownership of that object to somebody else. The code in this state right now, when it gets to the bottom here, is going to start calling destructors on the trainer class. So these two trainers here have been declared as stack allocated variables. So when they go out of scope, in the main function, when we return from that, their destructor is called. When this goes out of scope, Pokemon Pika, when that goes out of scope, its destructor is also called, and what was allocated for it is being released. When we've got the main function trying to release Pika and the trainer trying to release Pika, both of them are trying to release that allocated memory. And because both of them are trying to release that allocated memory, we get a seg fault. We get a seg fault. We get a seg fault. Is the, by the way, I changed this to like a light theme. Is that a little bit easier to read than the dark theme? It's the same? Okay. Well, whatever then. I'll just blow your eyes out watching bright screens. Okay. So we get a seg fault. Let's actually step through this really, really quickly here. So we've got LLDB test trainer. I'm going to run this through my debugger. I'm going to break on main in this. I'm going to run it. And what I want to do is just step through a couple things. So I'm going to go to the next line, the next line, the next line, the next line. I'm going to step into this function or into this method. So I'm stepped into add Pokemon here. And going through this, here's where we're basically saying, well, we're going to take ownership of this now. So I've copied this pointer into my array of pointers to Pokemon. And I'm going to keep going here. I'm just going to say next a couple times. I'm going to skip over it this time. I don't really need to step through that method again. And I'm going to run this line. So this is line 41. I'm at the closing brace. I'm at the closing brace of the main function. I'm going to step now. I'm going to step into methods. When I step into methods now at the closing brace of the main function, we're going to start calling destructors of the objects that are going out of scope here. So the first thing that's going out of scope is a stack allocated Pokemon. You can see here it's calling the Pokemon destructor. There's nothing in there, so we just know that it's being released, but nothing's really happening inside the destructor itself. I'll press enter again. This gets us back to where we were before. I'm going to press enter again. This is also going to step. Now we're in the destructor for the trainer class. So one of those trainers is going out of scope. So now we're in that destructor. And here is where we start trying to destruct Pokemon, which has already been destructed. The first destructor that was called was the first Pokemon that we added to this. So when we try to call delete again, this is where we're getting that seg fault. So our goal now is basically we want to go through the process of taking actual ownership of this instance by making a duplicate of it so that we own it. And it's the responsibility of the caller to keep ownership of their own copy of that Pokemon object. So let's take a look at trainer.h and trainer.cpp. What I want to do here first is I want to change this to a reference. I want to change this to a reference because I'm saying I'm going to take ownership by copying this thing, and I want to make it a little bit easier for myself to call the copy constructor in this add trainer or add Pokemon function method. I also want this to be a const Pokemon. I'm not going to make changes to the one that you have passed to me. I do not want to make changes to the Pokemon that you passed to me. I just want to get a copy of this thing so that I can copy it myself, to have my own copy that I own personally, all by myself. I'm going to save that. And in the trainer class, in add Pokemon, I need to make the same changes to my signature. So const. I'm going to change this to Pokemon, ampersand, and to add. So I'm now taking a reference to a Pokemon. It's not a pointer to a Pokemon anymore. I'm taking a reference to a Pokemon. So I'm taking an address of a Pokemon. Because I'm taking the address of a Pokemon, the one place where I am using that arrow notation to dereference my pointer. I need to change it into a dot. I don't use arrows for reference types. I use dot notation. And then the rest of this is going to be that what I want to call here is I don't want to have a copy of that pointer, but instead I want to dynamically allocate my own Pokemon. I want to get ownership of this thing, so I'm going to make my own Pokemon that's a copy of the one that you passed to me. In the Pokemon copy constructor, so I've got this Pokemon, const Pokemon, a reference to a Pokemon. So here I'm going to say, instead of just to add, new Pokemon to add. So I'm calling the copy constructor here, and I'm doing dynamic memory allocation. So create a new instance of Pokemon and then use the properties from this one that I'm passing to you to copy everything into it. And now I own this thing. Let's try make this. It's not going to work. It's not going to work. It's not going to work because we're calling a method here toAdd.getNickname. This is a method that's acting on the Pokemon class. So let's take a look at Pokemon here. Pokemon has this method, getNickname. As declared here, this is it's a method on the class. But there's no statement about whether or not it makes changes to the properties of that class. Because there's no statement about whether or not it makes changes to properties of that class, our compiler is basically saying, hey, you said you weren't going to make any changes to this thing that was passed to you. You told me that. You said you're not going to make any changes to this thing that was passed to you. But you're calling a method, and maybe that method has side effects that I don't know about. We know that this method has no side effects. It's an accessor. It's just giving back the value that we have in that property. The way that we can tell our compiler there are no changes to the properties of this class is to mark this method as const. So add this const to the end of the method declaration. And now this is saying the method that you're calling will not make changes to the property. So when I call this method, it's not going to change anything about the Pokemon class. It's just going to give me back a value. So I'm going to go to Pokemon.cpp, and I'm going to make the same change here. So get nickname, I need to mark this const so that, again, the compiler knows I'm not making any changes to the instance of Pokemon that's being referred to here. So I'm going to try and make this again. Undefined reference to get nickname ABI CXX11. In Poco printer print. I'm just going to delete this class. I'm just going to delete this class. We're not using it for anything anyway. Undefined reference to. Do something wrong here. What did I do wrong? I keep finding myself in this state. I keep finding myself in this state. Did I miss something here? I gotta bail out. I gotta bail out. I'm going to delete this class for now. We're not using it anywhere. We're using it in main.cpp, which we're not actually using right now. So what I'm going to do is do that. Okay. Good. This is kind of where I want to be. So now in test trainer, what we've got is that we've got a reference value that we're trying to accept as part of this add Pokemon method. And what we had been doing here in test trainer was we've got this stack allocated Pikachu. We've got the stack allocated Pikachu. And to add a pointer to a Pokemon, we had to get the address of it, the ampersand address of it. But because we're taking a reference to this object now, we don't need to have this ampersand in front of this. We can just pass this stack allocated object and it should just work. It will take that copy of that object for us. In the other place where we're doing this, so Pikachu is a dynamically allocated heap variable. Here, this is a pointer to a Pokemon. It's not a Pokemon typed variable. The type of this variable is pointer to Pokemon. To get the actual instance of that class, we have to dereference this object. So I'm going to put a star in front of this, and this is going to dereference that object so that I can pass into a referenced variable into that argument. So this works. This solves this problem here. And what I want to do here is run test trainer through LLDB one more time. This time, I'm going to break on line 19. I don't want to stop at main. I want to go to line 19, and I want to step into add Pokemon itself so that we can see that we're actually calling the copy constructor. So I'm going to break on 19. I'm going to run test trainer. And I'm going to step into add Pokemon here. This is the first Pokemon that we're adding to this. So there can't be any duplicates because there's nothing in the array of Pokemon that we've got yet. I'm going to go to the next line, and I'm going to step here. And by stepping here, I'm going to be stepping into the constructor for the Pokemon class. And the constructor that we're stepping into is that copy constructor. So you're using this reference type to pass into the constructor itself. We're going to initialize all the properties of this Pokemon class, and then we're going to go back to the main part of this. After we run this, what we were failing on before was that we got to this end of function and things were going out of scope, and we tried to delete something that had already been released. We had that stack allocated Pokemon. We tried to call delete on it because it was at the end of the main function, and we were getting a seg fault. And now what we should get is nothing. It's just done. We're not trying to delete the thing that we don't own anymore because we made a duplicate of it and we own it entirely ourselves. I'm going to quit this. We don't have to change anything about this test trainer file right now. We don't have to release anything in here anymore because we don't have to release anything new in here because Pika itself is it's a stack allocated object. So it's automatically released for us at the end of the main function. The one that was dynamically allocated, Pika 2, this one we all are already releasing at the end of this main function. Okay, so mission accomplished. We've got our trainer now taking ownership of instances of this Pokemon class. When the trainer object is destroyed by calling its destructor, it is releasing the resources of the pointers or the objects that it's taken control of, taken ownership of. And we were able to pass stack allocated variables into that function and not have our code seg fault anymore, Okay, so end of discussion for copy constructors. This is kind of where we're going to stop for copy constructors, and I want to move on to operator overloading. Are there any questions about copy constructors? This is all good? We're okay with this? Yes? Let's try it out. So this nickname at 0 is equal to, I don't know, That's a good letter. We're just not even allowed to compile it. So it's able to make our compiler is able to make some informed choices about what we're doing inside of a function that's marked as const. We're okay? All right. So when I was coming in today, I noticed that there was like no lineup of cars. And then when I was driving to my parking spot today, I noticed there's hardly any cars in the parking lot. I can't decide if that's just because of the time that I was coming in or what, but like I was coming in at 8:30 when classes start. And usually it's like the cars are all backed up all the way to Pembina Highway, all the way to Pembina Highway. Have you noticed that lots of people are missing from classes? Yes? Okay, so it's not just me then. It's not just me imagining that. Okay, I don't know. Digression. All right, so we've got copy constructors. Let's take a look at the last part of OCCF, which is adding an assignment operator. One thing that C++ gives us that is something that can happen in other languages is the ability to overload operators. So we think about this idea of overriding or overloading methods. C++ is also giving us the ability to define how objects should behave when we apply operators to them. We have the ability to replace the default behavior or to define behavior for operators with methods in classes. So we can say when you use the plus operator on an instance of this class, this is what you should do. When you use the assignment operator equals, this is what you should do. When you use the comparison operator equals equals, this is what you should do. This specific feature is why we can use equals equals on instances of string objects in C++, where we can't with Java. This specific feature is what's giving us that. This is actually really similar to something that you can do in Python. So I'm going to open up a link here. This is a link to the Python data model reference. Python has a list of these special method names that you can define on classes. And the special method names that you can define on classes are things like new. This is what you should do when you're constructing an instance of an object in Python, or init, or del, which is a destructor. But the more interesting thing here that kind of maps to what we're trying to do are methods like these ones. So lt, le, eq, ne, gt, ge. These are all operators. When you use these operators, greater than, like literally the greater than symbol or the less than symbol, these are the methods on an object in Python that are actually being called. So if you create your own class in Python that overrides these methods on the object type, it will invoke those methods when you use an operator on an object in Python. C++ gives us the ability to do this in a compiled language. This is not at all similar to Java. You can't do this in Java. This is not a Java feature. You can't do it. The best you can hope for is like having method names that resemble the operators that you want to use, but you can't do this in Java. The syntax is awful. It's really terrible. It is really, really just like painful to type all this out, but it is what it is. To do operator, specifically the assignment operator in C++, we have to have a method that returns a reference object, a reference to the type that we are defining in this class. And the method has to be named the word operator, so the literal keyword operator, the operator that you want to overload, in this case an equal sign, and then the parameter that you pass to this, the thing that's going to be on the right-hand side of the equal sign, this is the parameter that you're passing to this, which is also a reference to that type. You want this usually to be a const value so that you're, again, not making changes to it, just like you're not wanting to make changes to something in a copy constructor. In the method definition itself, so within the class definition itself, we use similar syntax to what we're doing with methods. equals here is just a method. It's just a method that's being invoked on an object. It has a return type, which is a reference to the object that you're defining this on. So it has that ampersand there. This is one of the few places where you will be returning a reference to an object. You use the class name, the 2 colons, the keyword operator, so the name of the method, which is this whole thing, the const reference to the thing that you're actually doing the assignment from. And then you do pretty much what you do in the copy constructor. You copy the properties of that class instance into the thing that you have right now. And finally, you return a reference to the object that you have just made changes to. So you're making a reference to this. This is a really weird idea. This is a really, really weird idea. The assignment operator and the copy constructor are similar to each other. They're very similar to each other. I'll get to you in just a second, okay? They're very similar to each other. The difference between the copy constructor and the assignment operator is that the copy constructor is allocating new memory for an object. The assignment operator is existing memory. You're mapping these properties onto existing memory, memory that has been already allocated for this object. Yeah?
So in this case, operator equals, it's not like equals 0, it's equal sign, and you're changing the operator of...
You're changing you're giving meaning to the operator equal sign for this object, for this class, yeah.
Then you read in the variables from the 2 classes into that method, and then you do whatever it is that you do, and then you return the reference?
So in this case, you're just going to use this, use it like an operator? You're just going to use it like an operator. I may be misunderstanding what you're asking, though.
Like you can make the behavior inside the method anything that you want it to be?
Yeah, anything you want it to be, because it is just a method. So if you want to print stuff out when you're in this assignment operator, you could do that, which would be really weird to do and not a good choice, but you could do it because it's just a method. Okay, good. So what I'd like to do here is I want to add this for a class where it doesn't really have a lot of meaning, just so that we can get through it fairly quickly and demonstrate the purpose, or demonstrate using it in a more realistic example than what we have here. So the way that I want to do this is I'm going to add this to the potion class. The potion class, remember, is a class that extends that type item. So potion is down here. I'm not going to add this to the super type. I'm just going to add it to this class. And I'm not going to do anything else other than adding it to this class. So to add an assignment operator to that class, again, the syntax is really, really weird. Object ampersand, in this case it would be potion ampersand, operator equals, in parentheses, const, the type that we want to use for assignment, and then the const type. So I'm going to say here potion ampersand operator equals, I spelled it wrong, operator equals, and what I want to take as an argument to this method is a const potion ampersand, a reference to a potion instance. In my potion class itself, in the definition, I'm going to pop this over to the side. I'm going to add this. So I'm going to say potion reference. This is my return type, the name of the class, 2 colons, operator equals, and what I'm taking as an argument is const potion other. There are no properties in this class, so there's nothing for me to really copy, but I am going to return this. I don't have to put this in parentheses necessarily. This is more for me to help myself when I'm reading this. I just have to return a dereferenced pointer to this. So it's a reference object that I'm returning. So I dereference the pointer that I have, which is this. This is a pointer. I am, however, going to do that bad thing that I said. I'm going to print a message here in assignment operator. Assignment operator for potion. Don't do that. Please don't do that. Please don't actually do that. But just to kind of help us see what's going on here, I want to do this. So I have this test item class. So I'm going to open this up here onto the side. And what I'm doing in test item here is creating instances of this class dynamically and using casting, dynamic cast in C++ to work with this. I'm going to make a couple of other potions here. So I'm going to say potion P1, potion P2. And I'm going to do this really interesting thing. We're going to say P1 is equal to P2. I want to call that assignment operator. I want to call that method that I have just defined on this class. I'm going to run this. And I'm going to run this again through the debugger. I don't really want to have just output here. I want to walk through the flow of what's happening as we're doing this. So I'm going to run through, test item was not recompiled because I don't have it in the make file anymore. So let me just quickly add this. Go all the way to the top. All the way to the top, okay. I missed a single L, and this is what I get out of that. I missed this single L at the end of this end L. I don't know if it's clear from you all sitting in this class. C++ is not my favorite language. I do prefer C to C++. It's simpler. It's so much simpler than C++ is as a language. Now we need to have language fights at the front of class. Okay, so I'm going to run LLDB, and I'm going to run it on test item here. In test item, I'm going to break on main. This is the very first thing I want to do. I want to step through this entire implementation. There's not much here, but I want to step through it to see what's going on. So I'm going to break on main, B main. I'm going to run this program, and I'm stopping at main. The very first thing I'm doing here is assigning to this pointer to item an instance of this potion class. This is not going to call an assignment operator. It's not going to call an assignment operator because we're not assigning to a potion. We're not assigning to a potion right now, so it's not going to call an assignment operator. I'm going to go past this line. This is calling the constructor for those two objects, and now we're on this line that's assigning an instance of potion to another instance of potion. If I step into this, it's going to start running that method that we just defined. This is the method that we've defined for the assignment operator. So I'm going to get this print out statement in assignment operator for potion, and then nothing's going to get copied because we didn't actually have any values to copy between these things, but that's fine. That's fine. We would do what we were kind of doing in the copy constructor by duplicating all the values of the thing that we're assigning in that method. I'm going to step out of this. I'm going to keep going past this. And now we're on line 19. On line 19, we have potion P is equal to dynamic cast potion pointer X. This is not going to call the copy constructor. It's not going to call the assignment operator. It's not going to call either of those things because this object is not, it's not an instance of a class. P here, the type that this has is pointer to potion. it is not that class name. So we're not going to use the methods that are on that class when we are using or referring to that. So let's give that a try. So I'm going to quit this. And what I'm going to say here is P is equal to, and what I'm going to say is P1. So I'm going to use one of those stack allocated variables. I'm going to make that. It's syntactically valid. It's syntactically valid. Let's run it through our debugger again. I'm just going to break on line 19 this time. I'm going to run it. So we're there. I'm going to hit N to go to the next line. I'm going to hit S. And there we are. So yes, by dereferencing it on the left side of the assignment operator, what we've said is I have an object of this type. So I'd like to call a method on it, which is the assignment operator method. So this statement here on the left side of the assignment operator turns this into an instance of that class. So when we have the assignment operator beside it, we're calling methods on that instance of that class. So big difference. The big difference between copy constructor and assignment operator, they function approximately the same. They're both going to be copying properties from some other object into an object of that type. The difference between the two of them is that the copy constructor is in the process of making an instance of that. It's allocating new memory for this thing. The assignment operator is operating directly on existing memory. It's making changes to something that already exists. So no new allocations are going to happen. This is just going to replace what's already there. We're okay with that? Okay. Yes. Yeah. So when I do a copy constructor, so if I don't have a copy constructor on this class, but just for the sake of discussion, if I do that, so let's go back to Potion, and I'm gonna add this constructor. I'm not gonna compile it. So let's say we have this copy constructor. On line 13, we're allocating new memory for P2, and then we're copying stuff from P1 into P2. On line 20, we're not allocating new memory. What we've dereferenced at P exists already. It's been allocated by something. So we're just going to copy from something else into that existing memory. So there's no new allocations that are happening there. Good. I'm going to set this back to the way that it was before. Yeah.
So does it not take ownership then if you would do that? Like we kind of talked about when you're doing a copy constructor, you can take ownership of something.
Yes.
If it's not making new memory, does it not do that then?
So by doing the assignment, because you're just reusing existing memory, you're still reusing the same address and everything. Taking ownership here, when we're talking about using the copy constructor, we're basically saying, I'd like to allocate new memory that I specifically own. Doing just assignment like that would mean that I'm just going to reuse something that exists already. So it's not going to be giving me the ability to own that address anymore. Yeah. Okay, good. Good, excellent. We did this. Okay, great. OCCF. I'm not going to say it again. I don't have to say it anymore. Yeah, yay. Good for me. Yeah, okay. So let's start talking a little bit more about some theory. A lot of what we're going to be talking about here is terminology to describe ways that we can do inheritance. So there's not going to be any new syntax here. I'm not adding any new syntax to what you know already. with one minor exception. I will add one minor thing to the syntax that you know already, but it's not like a huge burden to figure out what this thing is. We're going to be talking about inheritance. And one of the things that we want to talk about when we're talking about the relationship between a class and a subclass is whether or not you can substitute the subclass for the superclass. Substitution here basically means we've got this idea of static type binding and dynamic or runtime class binding. We have those two ideas, and we have a pretty good idea of what those things mean. Dynamic class binding implies that we can assign values to a static type that have different subclasses of that type. Substitution is this idea that I can take any subtype of a class and just put it in there and call methods on that supertype, and I should expect the same behavior across all implementations of the subtype. This is something that's called Liskov's substitution principle. That's Barbara Liskov. She's like 83 now. She's quite old. This was, I think, 10 or more years ago that this photo was taken. But she's out of MIT, and she's doing like language design and software engineering. And the idea that she had, which is Liskov's substitution principle, we've got static typing and dynamic class binding. I should be able to have any subtype of that supertype, drop it into or bind it to the value of that class, that variable, and it should just work the same way for any of the methods that I call on the supertype itself. Here's an example of something that satisfies Liskov's substitution principle. If I've got this supertype shape, it's an abstract class, and I have these two subtypes, triangle and square. I'd like to think that we can all agree that triangles are shapes and squares are shapes. Yes, yes, good, good. Okay, good, yes. These two things are shapes that have an area. In a program, if I declare something that has a static type of the supertype shape, I should be able to assign any of its subtypes, bind any subtype to it, and it should just work. I should be able to expect it to work exactly the same way. So when I assign a new triangle to this static type shape, and I print .getArea, I call this method that's defined in the supertype, I get a floating point value. When I reassign it to this type square and I call getArea, it should just work. I get a floating point value. This satisfies Liskov's substitution principle, because when I call this method on the supertypes class, the subtypes answer it, but I'm getting the same behavior. I'm not changing anything about the way I'm interpreting that. It just works the way that I expect it to. If you've never watched Adventure Time and you have time to watch Adventure Time, you should watch Adventure Time. Is it about Adventure Time? Okay. Should the instance variable match all subtypes? So what do you mean by that? Can you? Okay.
But some of them have extra.
So let me try to put it in this term. Say you have like an integer in the shape class, and then an integer, I don't know, shape ID. And then in the subclasses, you have float shape ID. Is that what you mean? Okay. So this is something that really only applies to the interface of the class. So the instance members are usually not part of the public interface of a class. The public interface here meaning the methods that you are allowed to call on that class. Because instance variables are usually something that you should be encapsulating, so hiding using private access modifiers, they're not usually part of the public interface for a class. So Liskov's substitution principle usually only applies to the public interface and not to instance variables within the class. So triangle and square here would have two different sets of instance variables. One would be base and height, and the other one would be side length, right? Because it's equal for all four of them. Okay, so this is something that satisfies Liskov's substitution principle. And this is a counterexample. This is an example of that similar hierarchy that does not satisfy Liskov's substitution principle. So we're extending shape with rectangle, and rectangle has two methods attached to it, set height and set width. We noticed, hey, a rectangle is a four-sided shape, and a square is also a four-sided shape. So let's just extend that class. The problem here is that we also thought we were being really smart and having this optimization of just call set height and I'll set both properties. And I'm not going to do anything in the set height method anymore, or the set width method anymore. So we've got these two methods on rectangle. We're replacing them in the subclass. We're saying set height is going to set both properties, and then we're not going to do anything in this subclass for set width. The problem with this is, the reason that this does not satisfy Liskov's substitution principle is that when I call the method on the supertype, so the rectangle supertype defines this method set width. When I call it, there are no changes to the instance. Nothing happens. It's an empty method. There's no changes to the internal properties of that class. There's no change to the state of that class. Because this doesn't have any change, and then calling the area method won't work the way that we expect it to. So when we have area for rectangle, it's length times width. When we have it for square, it's just going to be width and height. It's not going to work the way that we expect it to. This violates Liskov's substitution principle because we can't just put in place of a rectangle an instance of square and use it in exactly the same way that we can a rectangle. As we look at these different kinds of ways to do inheritance, we're going to have to make this decision about whether or not this type of inheritance is substitutable or not. So can we use this type of inheritance? And can we use it, and can we say that we can substitute subtypes within this type of inheritance with these properties to satisfy this principle? Are we okay with Liskov's substitution principle before we move on? Because it kind of hinges on everything here. Yeah. If we implemented set width, sort of. The problem that you have with implementing set width is that it's changing two things. So what I mean by that, I'm actually going to pop this into VS Code so I can edit it, because I want to answer your question fully here. Please ignore all the red squiggly underlines because this is not a valid Java file. So your suggestion, it's a good suggestion, and I can see your line of thought here. What if we just say height equals width What if we do that? Sorry, this should also say width. What if we do that? That's what you're suggesting, right? Okay, good. That's good. The problem is that when I say rectangle R, I'm expecting that calling one method only affects one of those properties. So I'm also going to put onto this superclass public int get height. I'm going to put accessors for the properties within this class. When I'm working on this as though it is a rectangle, when I say r.get height, I'm going to actually do this properly. Set height 40. I'm expecting that r dot get width is 20 and r dot get height is 40. That's my expectation that's kind of defined by the interface of rectangle. Calling one of those mutators only affects one property. But because the square implementation of it has modified both of them, we're violating that principle because it's going to have effects that we're not expecting to have from it. Yes, in the square implementation. But our expectation from the supertype is that it shouldn't make those changes. This should change different things about an instance of this class.
Principle that you just defined, it's only supposed to like take away the definition of it down. Does that make sense? Because if it became a square, then that is expected.
So if we change this to square r, then yes, that's expected. And I would expect that calling this in each of those cases, but that's the expected outcome.
So like it's okay to take away the functionality or like to streamline it if we're going down in class hierarchy.
If you're using that specific type, then yes. But if you're going upwards and you're trying to replace instances of rectangle with instances of square, then it doesn't work anymore. Yeah. A better solution to this would be to have like an intermediary quadrilateral or something, four-sided shape, or I don't know what would be a four-sided shape that's a rectangle and a square. Is quadrilateral, a four-sided shape, and then have just set for the square type and then two set properties for the rectangle type instead. So that is, thank you for saying that. That's a really good idea of how to fix this, but it still does violate Liskov's substitution principle because the behavior is different when we're working with that supertype. Okay. Any other questions? Okay. All right, so get ready. We're going to go through a bunch of different ways to use inheritance. There's only one place where we're going to describe new syntax, and the new syntax is in Java, and it might be something that you've seen before. The one place that we're going to be looking at possibly new syntax in Java is for specification, and we're going to be taking a look at the interface type in Java. Have you seen interfaces before? Anybody? Just a couple people, but not in school? In classes? Have you seen it in classes anywhere? Okay, so in high school, so not in university. I should specify university courses. Okay, good. Our 1020 curriculum has changed to add interfaces, so I'm just making sure that you didn't take that version of 1020 yet. And I'm just like repeating stuff that you've seen before again and again and again. So let's take a look at these different ways to do inheritance. We're going to be thinking about whether or not subtypes and supertypes can be substitutable according to Liskov's substitution principle. And in some cases, we're going to look at examples of code. In other cases, we're just going to be describing this idea because it's sometimes something that you have seen before and just giving a formal name to that something that you've seen before. Specialization. This is the first form of inheritance that we'll be thinking about. This is the one that you have seen before over and over and over and over again. This is that is-a relationship that you have, and it's the most common form of inheritance. When you have a subclass of a superclass in this specialization form, it may have more instance variables, it may have more methods, but it's just specializing the supertype that you've got. Subclasses in this relationship are generally substitutable. So they haven't made any changes to the behavior of the superclass. They're not overriding anything necessarily. They're just adding new stuff to it. So they are substitutable for the parent class. It may override existing behavior. It might override existing behavior. But this is going to be something that would still need to satisfy Liskov's substitution principle. So if we have a shape supertype, and then from that shape supertype, we have a sided shape, and then we have a quadrilateral, and then we have square and rectangle, and then we have triangle. I didn't put that in here. If we have that, oh man, this is a bad example. It's a bad example because I didn't actually put it in here. If we have this hierarchy, this is going to make more sense than what we had before. Yeah, okay. Specification is a can-do relationship. So where specialization is an is-a relationship, we have a supertype and we have a subtype. The subtype is an instance of the supertype. Specification is more about behaviors that we're specifying on a type as opposed to the relationship of kind of inheritance. The way that this looks is that we're specifying just behavior in the superclass. We're just specifying behavior and nothing else. There are no instance properties in the superclass. The only thing that we're doing is specifying behavior, the methods that this thing can do. In what we have right now, both Java and C++, this is of the form abstract classes, where the abstract class itself doesn't have any instance variables. This is a form of specification. We're saying things that implement this class, things that extend this type, can do this method. So we have these printable things, and we have methods that we can get data from. Specification is a specialization is a specialization of specialization. Specialization is we've got a supertype and we've got a subtype, and we are saying that the subtype is implementing behavior from the supertype or making changes to or adding to. Specification is just a specialization of this by saying we're only allowing methods to be defined in that supertype. That's all we're saying. There's just behaviors in the supertype. This is substitutable for the parent, so it conforms with LSP. The place that we have done this before, we have done this in this class. We've got this specification relationship between things, and that is in that item and potion relationship. So in item, we've got really just this ability to apply. So we've got a couple of other things that are like type and stuff, but the only thing that we've really defined in this supertype is this method apply. We're saying that things that extend this class can apply to a Pokemon. That's what we're saying by doing this. So having this potion type here, having that extend this item class is basically saying we are going to have this apply behavior, and our supertype doesn't really have any information in it beyond saying that I can call this apply method. In test item.cpp, we use this in a couple of places by calling these methods like print, and we use this in another place. I believe it was in test trainer.cpp where we applied it wasn't here. Where was it? It was in the main function where we applied a potion to one of the Pokemon after we attacked it. So our item and potion relationship here is a specification relationship. Item is a class that's specifying what classes of this type can do. Potion is an implementation of that. It implements the methods that are defined in that supertype. So far, we've only seen abstract classes as a way to do that. Java has another method for doing this kind of relationship between classes and another way to implement this specification thing. In Java, we have this thing called an interface. An interface is, it looks really similar to a class. But all it does is specify methods, and all methods in this interface type are defined as public. They're all public methods. Declaring an interface is similar to what we do with a class. We say public interface, and then the name of the interface that we want to define. We have methods within that. We don't have to add access modifiers to those methods because they are all public. All of these methods are public. We don't have to have access modifiers here. It doesn't really make sense to have private methods on an interface because what we're trying to define here is the public interface for something. When we want to use that interface, so we don't have to mark this as abstract, we don't have to mark it as public-private, it just is public by default. When we say that a specific class implements an interface, we use this implements keyword, and then we have to declare and define the method that we have defined in the interface for that type. Java has the ability to implement multiple interfaces. In C++, we have this idea of multiple inheritance. We could have supertypes and supertypes and supertypes, and we could have a single class that extends all of those supertypes. We do not have multiple inheritance in Java, but we can implement multiple interfaces. So let's take a look at what that might look like. I'm going to make a new file here that kind of resembles what we've got with our Pokemon examples, just to keep it with something that we're familiar with. Item is something that I would probably declare as an interface in Java. I would declare this as an interface in Java because this is really only going to be, this is behavior that you can apply to something. In this interface, if I'm going to stick with what we have already in our Pokemon example, so let me pop this header file open for item. The one thing that I want to be able to do here is I want to be able to apply this to a specific Pokemon. So I don't provide an implementation of this interface. I don't provide an implementation of this interface inside the interface itself. This is going to be on a class that I'm going to say implements this interface. And I would say public class potion implements item. And then I would say something like public void apply Pokemon to apply. And then within this implementation, that's where I'd actually provide what this implementation is for this specific item. I can use this interface type as a type. So in the same way that I'm using it as an abstract class here, I can use this interface as a type. So somewhere else I can say item X is equal to new potion. One thing that changes from class extension to interface implementation with Java is that we can implement multiple interfaces. I can do something like this. I can say that potion implements item, and it implements this comparable interface. Comparable is one of these generic types. So we use these angle brackets to say which type we want to be able to compare this thing to. The comparable interface, the method that we have to implement that's part of that interface is compare to, and it returns an integer. And then we do some comparison and return, let's say that we're just going to return them all as equal here. Because this one single class implements both interfaces, I can use that one single class in replacement of both of these. I can do this in Java. This is allowed in Java because these interfaces do not have data attached to them. There's no instance variables inside of an interface. The problem that we have with multiple inheritance in C++ is that when we have actual implementations of methods and actual implementations of instance variables, it's unclear which of the supertypes we're actually getting that thing from. Interfaces, at least right now, don't have implementations of methods. They don't have implementation details at all. There's no instance variables inside of an interface. If item happened to also have something like int compare to. If our interface item also had something like this, it doesn't matter, because all we're saying is that this class that implements this interface will have this method. That's all we're saying about it. We're not saying what the implementation is, just that it has an implementation of that method itself. Okay with that, interfaces? It's just like classes, but light. There's no implementation details here. So we have just a definition of what this class can do. That's it, nothing else. Not what it is. All we're saying is this is what this class can do. We're specifying behavior for a specific class. Another form of inheritance is to extend an existing class to use its structure, and what we're calling that is construction. Here's an example. I've already got this really cool array list in the JDK. Somebody else has done this work for me, and I would like to implement my own kind of list. I would like to implement my own kind of data structure. But I'm really lazy, and I trust the Java developers to have built something robust. I believe that they will have done this correctly. By extending array list, what I get is a complete implementation of an array list. I get all of the instance variables in the superclass. I get all of the behavior from the superclass. Here's my own type. My own type is called counting list. And what I want to do with counting list is keep track of how many things have ever been added to this list. I override the add method that's defined on ArrayList. I call super.add, and I pass that item because the ArrayList implementation has this add method that I can call, and it will make changes to its own internal state. And then I increment this counter that I have, keeping track of all the items that have ever been added to this. Here's my question to you. Take a minute to think about this, 30 seconds. Based on this code, are there any bugs in this? Does this do what it says in the box? There's a syntax error, sorry, that add should have a return type, not just public add. Outside of that, if this class's job is to count everything that was ever added to it, yes, this has a bug. Thumbs up, please. No, this does not have any bugs. It's fine. It will work. What do you think? So got about 3 thumbs up, 2 thumbs down, and lots of people looking at laptops. Good. Okay, great. I can't even spell ArrayList right today. Here's the JDK for an array list. Here are the constructors. This is part of the public interface for ArrayList. One of them accepts as input a collection that we haven't accounted for. So I don't know that these things were added because I didn't override that constructor. Here's my add method. We'll just pretend that I put Boolean on there. Here's another add method. Here's an add all method. And here's another add all method. By extending this class, So yes, we get that class for free. We get the whole implementation of an array list for free. The goal that I have with this counting list class is to keep track of the total number of items that have ever been added to it. I don't care what the size is right now. I just want to know how many things have ever been added to it. I get all this stuff for free, but I forget to add this behavior that I want to all of the F methods that can be used to interact with this. The public interface that I get from the class that I extend for construction is my public interface too. If I call add all on counting lists, then I will get what comes from the superclasses implementation. If I call add at a specific index, then I will get whatever comes from the superclasses implementation of that. So the answer here is, does this code have any bugs? Yes, it doesn't do what it says in the box. Another approach to this, or another alternative to this counting list, is I've got this array list class, this implementation that provides a list implementation, and I want to use it for a queue. I only want to provide insert, push, and pop operations on my queue or a stack. I just want to provide 2 operations on this thing, but ArrayList has implementations for all sorts of other stuff. We're running out of time, so I'm just going to skip ahead, and you can see the state of my life right now, and I will see you all on Tuesday next week. Bye, everyone.